All right, and if you would, please make sure that your video is unmuted and that your microphone is muted. I can hear a couple of you moving around, getting settled, and that's all cool, but it comes over the rest. Okay, so good to see you all. Again, if you please would take your video down so I can see that you're there and see your happy face and see that you are well. I hope that all of you are well. Let's get this fun stuff out of the way and let's get down to business. All right, let me do one more thing and then we will get rocking. Okay, here we go. Here's our map check. This is what we're going to do today. We're going to jump into hypothesis testing with how to do hypothesis tests. The way that I have this broken down is into 3 chunks of 4. So I'm going to explain a little bit more of what all that means as we go along. But the bottom line today we're going to focus on proportion hypothesis testing. It's a good place to start. A lot of folks get hung up on what proportions are, so we might as well start there. It's not the toughest type of test, but it's somewhere in the middle. So we'll do that today. No homework this weekend, but obviously you've got the Way of the Warrior project due on Tuesday. That's Canvas at no later than 7 p.m. And then looking ahead to next week, we'll get the other 2 chunks of hypothesis testing. So on Tuesday, we'll go over proportion means where we know the standard deviation. We understand that sigma. And then Thursday, we'll get into hypothesis tests where we don't know what the standard deviation mean or the standard deviation is of the proportion mean. Okay. Now, somewhere here really soon, probably within the next 24 hours, I'll go ahead and post the Pearson work for this entire block. It'll be the last Pearson that we're going to do. No need to fret or worry about it. It's not due again this Sunday. It's due a week from Sunday. But I want to open it so you've got maximum amount of time to go ahead and work on it, get into it, start getting some reps in so you don't lose that mental muscle memory. Okay. Any questions on this? All right, super. Let's rock and roll. All right, here's what we're going to do today. Recording, I already got that going on. Let's see what we got here. I want to talk about all types of hypothesis tests and then just focus on, we have 2 methods of hypothesis testing. Okay, so I just want to it's kind of like going to Disneyland. You're like, holy cow, there's so much to this. But then you say, okay, I'm just going to go to Adventureland and hang out there. But when you're hanging out in Adventureland, you know there's more to the park than just Adventureland. But the beautiful thing about this, in contrast to Disneyland, and I'm not a big fan of Disneyland, is that there's really a short list of problems that I could give you, okay? And this is what I'm talking about. So when we talk about the different types of hypothesis tests, at least that we're going to do in this course, there's really 3 big chunks. There's population proportion hypothesis tests. That's what we're going to do today. That's why that's highlighted. There's population mean hypothesis tests where we know sigma, the standard deviation. That's what we're going to do next Tuesday. And then the population mean sigma is unknown. And that's what we're going to do next Thursday. And you're probably thinking, you just told us that. I know. But what I'm trying to do with this slide is get you comfortable knowing that, hey, I really just need to know how to take down somebody 12 different ways. And if that 12 is kind of intimidating to you for now, then you really need to know just kind of, again, 3 forests. Okay. And being able to identify those 3 forests. And once you're in those forests, what you're being asked to do. So I guess 12 is better than 16, which is better than 25. I guess arguably someone could say, well, 12 is still more than 11. It's still more than 8. I understand. But this slide and the next one are really almost a scoreboard for you. I would encourage you to use them that way. So in the next coming weeks, as you continue to get reps in and you build confidence and proficiency, that you can look at this and say, do I know how to do that? That yellow block, at least today it's yellow. Do I know how to do that middle block? All 4 ways. Do I know to do that bottom block all 4 ways? Yes or no? And then you can go from there. Pearson will help you get some reps in. We're going to do some reps today. But you know, you're in control of your destiny here, and it starts with your assessment of your own proficiency and confidence. Let's blow this up a little bit more without going crazy. And here's what I'm talking about. So when we look into the P-pop forest, this talks about the type of distribution we could use. And there's only one distribution in the P-pop forest. That's what's beautiful about it. We don't have to worry about the T distribution there. We could do a one-tailed test, or we could do a two-tailed test. And then we have 2 methods at which we could do both tests. And there may be some of you that are like, oh, okay, you've already lost me. Don't worry about it. I'm just showing you this. If it's not going to make sense right now, I'm just showing you Disneyland, the big park. Okay. And remember the first time you ever went to Disneyland or Disney World or some kind of imitation place? I know when I was a kid, we had Worlds of Fun because I lived in Kansas City and we'd go there every summer. You're kind of like, holy cow, how am I going to be able to do all this stuff in the amusement park today? Well, don't worry about that right now. Today, we're just going to work on a section of the park, and then we're going to build from there. But the beautiful thing is that the competency that we gain today will transfer to the other sections of the park. It's not like all these are separate islands. Quite the contrary, they all feed off of each other. So once you get, for example, the critical value method down, you can use it anywhere. Once you get the p-value down, the method down, you can use it anywhere, and so on and so forth. So there's that. And with that, let's get on into a couple more things before we begin. First is this document here that's on your Canvas, both from Tuesday and today. And so I wrote this a while back, and this is just kind of a primer. All it is like a page, barely 2 pages. Okay. And all it is just a way to think about hypothesis testing. I know the other day we start to get into the null and the alternative and how do we come up with this and that, and it starts to get kind of overwhelming. This is just a simple way to think about hypothesis testing that I wrote last year with my last class. And you know, sample size of 1 is not very much, but one person said, hey, this really helped me out a lot. So it may help you too. So there's that out there. And with that, let me just find my slideshow down here. All right. So here's what we're going to do today. And every time I mess around, all right. Sorry, I'm having some technical difficulties on my end. I don't want that there. Okay, I'm just going to drive on with it. For some reason, I'm just having, I don't know why, I've lost seeing all of you. Okay, we'll just continue on through it. All right, so today we're going to focus on population proportions. And I put this picture of a pizza. I've probably been eating too much pizza lately, but this is a way that might be helpful for you to think about what a proportion is in the first place. So when we have a whole pizza, that essentially is 1 or 100. And if we were to say, well, how many pieces of pizza are left? Obviously, there's not the whole pizza there. Well, we have 11 pieces. We count all these out of 12. So P is 11 divided by 12, whatever that is. Pretty close to 100, but it's not 100. It's like 0.9 something. So that's the way I like to think about proportions. It's not the whole, it's part of the whole. Okay. Whereas means are usually whole numbers. Now, the minute I say that, folks can say, well, what if we have a mean of 0.45 seconds in terms of data upload or something like that? Well, yes, that's true. But the contrast is not true. So I don't have a proportion of 560. That just kind of doesn't make sense. It might be 56%. It might be 0.56, but I don't have a proportion of 560 or 1500 or something like that. So, again, that may be helpful for you. I think it's helpful to me, but just all those devices in which you can think, okay, this is a proportion, you can recognize a proportion, you can understand what a proportion is. Okay, and again, this is what we're going to do today. This is, in fact, all we're going to do today. And we'll see how that goes. So within this section that we're talking about today, we're essentially going to do the same problem with a tiny little modification, and we're going to do it 4 different ways. And the reason we're going to do it that way, it may seem overly simple, but so that you have a good baseline to start out with. So with that, let's get introduced to our problem. Now, also before I begin, and I apologize for doing this at the last minute, these slides are up on your canvas. I meant to get them up there earlier so you'd have time to download them or print them. Things just didn't work out that way. But this version of the slide deck is on today's canvas. So the benefit of that is that you can work these problems later. You can copy your notes onto them, whatever way works. I'm a big fan of copying things multiple times, not to have double work, but because every time I copy it, it imprints in my brain more. So we are going to begin, just to be overt about it. This is a proportion population problem. And we are going to begin by doing, this is a 2-tailed test, and we're going to use the critical value method. Now, before we get into the problem, the other beautiful thing is that there are steps to doing the hypothesis test. And that's what this little box is down in the left-hand corner. There's a step list for the critical value method, and there's a step list for the p-value method. It gets even better. They're not that much different from each other. So we're just going to walk through this very deliberately so that you have that good baseline on how to do proportion population hypothesis tests. So let's look at our yellow box. According to a 2020 survey, 45% of US workers stated that they work during non-business hours. So kind of like this guy right here. I don't know. I think that's like Sylvester Stallone. I'm just kidding. So he works during non-business hours. He runs around at night and does some things. And anyway, he's got 3 movies under his belt, and maybe there'll be a 4th one. After a while, it's kind of like watching a video game. So 45% of workers stated that they work during non-business hours. Okay, who cares? Well, as an entrepreneur looking for a market of non-traditional workers, you have decided to conduct a new survey to see if this proportion has changed. Okay, so the problem doesn't state, let me get my pen fired up here. The problem doesn't state, sorry about that, leftovers. Problem does not state if you're interested in how it's changed. You're just interested in if it has changed. And that's why this is a 2-tailed test. If it was 1-tailed, you'd be interested in if it has gotten greater or if it's gotten less since the time this survey was done. Okay. So that's why we know it's a 2-tailed test. And here's the results of your new survey. I guess if it's done in 2020, then it'd have to be really new because we're, still in 2020. But anyway, 208 of 400 US workers reported they work during non-business hours. And so you decide you want to use a 0.05 level of significance. Okay, super. So let's use our checklist. First step, like we did the other day, state the null and alternative hypothesis. Now, and we're just going to get John out of the way because we need the space. So as much as that's a cool photo, we got knowledge to gain. So what I learned the other day is that maybe a helpful technique for some of you, as I state our null and alternative, is actually to state the alternative first and then state the null. That was helpful for a lot of folks. So we'll just give that a shot and see. But either way, we'll just give that a shot. So, Alyssa, what do you think is the alternative hypothesis here?
Would it be that they work during business hours?
Okay. No, it's going to have something to do with the proportion population, and we're going to write it mathematically. So, David, what do you think?
That this is for the alternative first, correct?
Yeah, either one, whichever you'd like to do, null or alternative.
For the null, you would say that 45% of U.S. workers equals like working during non-business hours, right?
Okay. So how do we express that with symbols and math?
That would equal your P-pot, correct?
Mm-hmm. So something like that?
Mm.
Okay. So Eric, what do you think our alternative hypothesis would be?
That the P-pop is either greater than
All right. So you're coming in a little broken. So the main thing I want everybody to center on is when we whichever one we do first, it doesn't matter. But if we're doing a proportion population, these two are going to be the same. And whatever number we put over here, it's the number associated with the null hypothesis. The alternative is going to be the same. It's this that's going to be different. And we will never have an equal sign or any variation of an equal sign down here in the alternative hypothesis. Okay? So that is step one. We have accomplished step one. Let's look at step two. Choose our level of significance and sample size. Okay? So we have our level of significance. All right? So alpha is going to be 0.05. And Justin, what is N?
The 208.
Okay. N is the 400. You're close. X, the characteristic we're interested in, workers that work during non-business hours, is 208. Okay. And so therefore, X divided by N is P, which we don't care about just yet, but we might as well compute it. So 208 divided by 400 is not a whole pizza. It's about half of one. Okay. So that takes us through level of significance. That's alpha, 0.05, because that was given to us right here. And our sample size, which is up here. So that takes us through number two. All right, number three, determine the appropriate test statistic and sampling distribution. Okay, now for all types of proportion population tests, this is very important, we are going to use the Z distribution, period. So I haven't thought of a cool phrase, P is Z, Z is P, with, if we're rolling with P-pop, we're rolling with the Z, whatever works for you. But we only have one option down here. If we've identified this correctly, which we have, we only have one option down here. That's the Z distribution. So that answers the distribution part. The test statistic is a formula that we know, we just haven't used it in this way because we still don't really understand what a test statistic is, but we will in a second. The test statistic is this. Sample P minus P-pop over P-pop times 1 minus P-pop over N. Okay, and we've used that before with sampling. Okay, when we sampled and determined P, we would use this to determine a Z score. Okay, so that's essentially what we're doing here. We're going to determine a Z score. All right, but right now what step 3 is referring to means make sure that you've got the right distribution, i.e. your handy dandy Z table, which I know we keep under our pillow at night. At least I do. I'm just kidding. I really don't. And that we've got our formula handy right here. Boom. All right. So cool. That takes us through step 3. All right. Let's look at step 4. Determine the critical value, rejection, and non-rejection regions. Okay. This is kind of a big step, but it'll come to us with habit. The first thing to determine our critical value is we need to reflect on the level of significance, 0.05. Okay. And theoretically, what we're doing is we're going to do this. All right. So I'm jumping ahead conceptually. We still have our P-pop here in the middle. We're going to determine regions. This is called a rejection region. This is called a rejection region. This is called do not reject. And when we talk about reject, we're saying that if this value, okay, falls either out here or over here, we are going to reject the null hypothesis. If it falls in here, we're not going to reject the null hypothesis. Okay, so to set up this architecture, all right, we first have to determine what's the value. When we say critical value, we want to determine what that is for here and what that is for here. It's going to be the same number, just this side is going to be positive and this side is going to be negative. Now you're probably going, a lot of work to do. Well, we have a little hack. So like I said, we need to remember level of significance is 0.05. And then I'm going to pull in a new hack table. Now this is on your canvas for today. First thing we got to differentiate from is, are we using a two-tailed test or a one-tailed test? We are using a two-tailed test. So we are over here. What is our level of significance? Alpha, 0.05. So our right value is going to be 1.96. Our left value is going to be negative 1.96. Now, before I go back, I got to remember, and that's what this skull is about, and our friend Mr. Cube, we only use this with number one, hypothesis tests involving population proportions, which is where we are today. So cool. We don't need to worry about number two. Okay, so game on. We can go right to this hack table. We don't have to mess around with the Z table or anything like that. We just need to know alpha and this critical value right here. So 1.96 and negative 1.96. So I'm going to go back here, pull my stuff back up. That means that this value here is 1.96. This value here is negative 1.96. So I've determined the critical values, okay, because it's two-tailed. I've determined the rejection region and the non-rejection region, okay? And you're probably going, okay, so what's the value that I'm looking at? Well, we're getting to that. But that right there, this diagram is step number 4. Let me just pause and see if anyone's got any questions so far. Everybody good? Okay. So number 5, collect the sample data. Organize the results, compute the value of the test statistic. Okay, well, we have the sample data. That's right there. 208 out of 400. We organize the results, so we have to do a little hidden step here and determine what P is, and then compute the value of the test statistic. Well, remember, the test statistic we're going to compute is this test statistic right here. Okay, so let's make sure we got our setup correct. P is 0.52. P-pop, what I like to call, is 0.45. We're going to divide all that by a square root of 0.45 times 1 minus 0.45 over 400. Once we do all this, consult with the chicken, we get a z-score of 2.814. We can also call this a z-stat, okay? So the reason we call that a z-stat, different from a z-score, it still tells us the same thing a z-score tells us, which is how many standard deviations, okay, 0.52 is to the left or right of the population proportion. But we don't necessarily need to convert this into a probability. We just need to compare it against that. Okay? So you're going to see Pearson and the text talk about decision rules. So a decision rule is the same thing as a rejection region. If 2.84 is greater than 1.96, it would fall out here. And so, Joel, what do we do with that? Do we reject the null hypothesis or do we fail to reject?
And so the null hypothesis is what again?
Right up here, HO, population proportion is equal to 0.45.
And the number you just got is
2.814.
So that would mean you have to reject it because it's not equal to 0.45.
Well, yes, we rejected, but it doesn't have to do with this 0.45 directly.
Okay.
The reason we set up these critical values was to set up these rejection regions. So the reason that we reject the null is because, go ahead.
It falls outside of the do not reject regions.
Yes.
Okay.
Exactly. And another way of putting that is it falls into the rejection region, which is simply another way of saying what you just did, what Joel just did. Okay? So based on it being out here in this blue area, we reject the null hypothesis. So we go back to our checklist. And we go down here, number 6, make the statistical decision, in parentheses, reject or do not reject the null. We reject the null. Now, number 7 is not in your text. I've added it because the so what is important. So Jennifer Miller, what do you think if we reject the null? What does that mean? What would we do now if we've rejected the null? What might we do now?
Accept our alternative hypothesis.
You know, it's really not the way it works. When we reject the null, we don't necessarily accept this, although we investigate this. But in a practical sense, Lexi, what do you think we might do now with this information?
Would you go back and say, like, that since it's not 45%, it's greater than that? say that it's a greater number of workers?
Yeah, so Lexi brings up a good point, and that's where a two-tailed test doesn't really help us as much, in my opinion, as a one-tailed. Okay, teaching this the second time now, I don't really know that the value of a two-tailed test is that it kind of fails to me in comparison to the one-tail. And here's what I'm getting at. Lexi brings up a good point, but we don't know whether it's greater or less. This kind of tells us that it's greater, but we didn't set out to do that. We set out to say it either is 0.45 or it's not. But in a practical sense, you know, we think it probably is greater because we're way the heck out here, which means that probably what has happened is that this population proportion has shifted and is probably somewhere way over here. Okay, which Lexi is getting at. In a practical sense, if we're looking for a market of non-traditional workers, we probably have grounds to believe that it has grown. And we should continue our marketing plan. We should continue to try to grow our business and find people like John Wick that work in the middle of the night. If we hadn't rejected the null, if we had failed to reject the null, then we might say, well, I mean, is 45% of people good enough? Is that enough of a viable market to continue recruiting non-traditional workers? Okay. But the main thing is that the so what is trying to put all this into the context of the problem with why did you start the investigation in the first place? What are you trying to do? So we'll continue to wrestle with that. Okay. Any questions on what we've done so far? Okay. I want everybody, and I will post my cleaned up version of this later so that you have that to refer to. Because I know once I get writing, I get kind of, I have a tendency to kind of go all over the place. For starting out, we have just done a proportion population two-tailed test using the critical value method. Okay. So now what we're going to do is we're going to do the same problem, but using the p-value method. So let's get rid of all that. Okay. All right. Same problem. Same problem. This time we have our checklist is and isn't a little bit different. Okay. So let's go down it. Our p-value steps, remember, that's the same, this has changed. Our p-value steps state the null and alternative hypothesis. Remember our null was that HO is that PPOP is equal to 0.45. Okay. Our alternative is that PPOP is not equal to 0.45. You'll notice that that did not change, okay, from how we worked this previously to now. Okay, cool. Let's go on to the second step. Choose a level of significance and a sample size. Well, we have alpha of 0.05, and we still have our same sample size, N of 400. Our X hasn't changed, so our X is 208, and therefore our P is 0.52. All right, cool. Determine, we're now here on step 3. Determine the appropriate test statistic in our sampling distribution. Well, because of this and this, we know we're rolling with the Z all day long. That's our distribution. And our test statistic is, say it with me now, P minus P pop over the square root of P pop times 1 minus P pop divided by N. And you may be thinking, nothing has changed. This all looks the same. And it is. Okay, so let's keep going. Collect the sample data. All right, cool. We have P 0.52. Compute the value of the test statistic and compute the P value. Okay. So let's do this first. Once again, when we put in all these values, 0.52 for sample P, we're going to put 0.45 into P pop. Same down here. We're going to put 400 in for N, and that is 2.814. That hasn't changed. Now, here's where the tricky part potentially comes in, but it's not that hard. To find the P value, okay, we are going to do, first, we can do it one of two ways. We can go to the Z table and look up 0.281. You know, I'm not too concerned about that right there. I'm sure Pearson is a little bit, but I need to do some reconnaissance on that. But I could go to my Z table to determine that, or I could do an Excel function, norm s dist, and put 2.84 in there. And this time I could do true or false. Okay. Now, what is this going to give me? Well, this is going to give me a value of 0.00726 and some other stuff. And again, this number here is referring to this area way out here. Now, if I do true, I'm going to get, you know, the 1 minus of that. So I could still do true and do a 1 minus, or I could do a false and get this. If I take this number and go to the Z table, I'm going to get a number that I'm going to have to do a 1 minus on. That number, if I go to the Z table for 2.81, is like 0.9975. Okay, and I suppose it's looks more than a little off. I guess not too much. So if I do this, I'm going to have to do a 1 minus to get something that looks like this. Either way, this is not the p-value yet. What I have to do on a two-tailed test, and this is very important, okay, is I have to double this. All right. I have to double it to get the p-value. And when I do that, I get something like 0.015. Okay. So let's make sure we emphasize that we have to double it on a two-tailed. And so all your smart people, you're probably thinking ahead. So when I do a one-tailed, I don't double this. That is correct. That is correct. But We're not there at one-tailed yet. We will be. Next question is, what do you do with this? Well, you have two things you can do with that. Let's remember two sets of numbers. Let's remember the p-value we got, and let's remember this number right here. Okay? So there's an old kind of a scientist saying, I think is actually kind of lame, but it goes, and it's written right here. If the p-value is low, then the null must go. And you're kind of like, boomer, what does that even mean? It should be written, if the p-value is lower than the level of significance, you reject the null hypothesis. Okay? So 0.015 is less than the level of significance, so you would reject the null hypothesis. Okay? I'm sure some guys in white lab coats came up with this and they thought it was so cool. I don't know. Here's another way of looking at it. Does the alligator eat the fish? Meaning, so we had, what did we have? Come on, pen. I don't want to erase all this. Man. So we had 0.05. We had 0.05 as alpha, and we had 0.015 as our p-value. So the alligator is going to eat the bigger value. And so if the alligator eats the fish, then you reject the null. Okay? Because I had a warrior who thought alpha looked like a fish, and so she came up with this. And like all sorts of warriors like were riding alligators on the exam and all sorts of things. So whatever one works for you. Okay? If this works for you and you can remember it, super. If the p-value is low, or if the p-value is low, then the HO must go. Either one or neither, whatever works for you. Okay, so let's bring all this stuff back up. That's why I didn't want to erase it, but to talk about the whole alligator thing. So we have alpha of 0.05. And that's what I like to do. Actually, let me write it differently. Okay, so I like to put alpha and put the little fishy here, and then I put p-value. Just to line all this up, and I park my p-value over here. And then I park my alpha over here. And I go, okay, which one does the alligator eat? Which one is bigger? Alligator's going to eat the bigger value. Alligator's going to go eat that. So if my alligator's eating the alpha or the fish, you can draw little teeth here, then I'm going to reject the null hypothesis. Okay? And again, the context is the same. Now, in terms of the two-tail, I still, I think that P, and again, my population proportion has shifted to the right because my test statistic is so far out here to the right. But why stop there? I could do a one-tailed test. Okay. The other thing I could do is, now that I've done this, I could go ahead and develop a confidence interval for what I think is the new population proportion. All right. And we'll not so much focus on this today, but remember, my confidence interval for the population proportion is simply P plus or minus Z over all that stuff. 1 minus p times p over the square root of n. And my z is whatever I want it to be, depending on the confidence interval I want to do. All right. The z up here doesn't have to do with any kind of z that I've used down here. But if I reject the null, then why stop there? I could go ahead and develop a confidence interval for that new, what I think the population proportion is. And that would be the equivalent of, if that red line, if I think the new population proportion is somewhere out here, that interval would be my butterfly net that I'm guessing where it actually is. Okay. But this here has nothing to do with this hypothesis test. This is just a confidence interval in general. But it is a follow through. Once I reject any null hypothesis, I could do a confidence interval for whatever I'm talking about. They're not the same thing by any means. They are related, though. So what we've just done is a hypothesis test for proportion population with a two-tailed method, a two-tailed test, and a p-value method. Now let's go into what it looks like with a one-tail. Okay, let's see what's changed. All right, this time we're going to do it again, proportion population, one tail, critical value. Okay, so we have some familiar faces now. All right, we have critical value, that's familiar. One tail, still not so familiar. That's what's changed. So right down here, I've highlighted in red, has increased. That's what you believe. So P-pop is 0.45, but you think that the P-pop has gone greater than that. So Jared, what would our null hypothesis be?
It would be P-pop is greater than 0.45.
Okay. It has something to do with 0.45.
Is it still equal to, or?
It has some degree of equal to in it.
Oh, is it greater than or equal to?
So when we think about this, this would be greater than. Okay. That is what our our alternative hypothesis is going to look like. And that's why I say it may help you all to think about, okay, what is my alternative, and do that one first. Okay. So if we read this right here, you think you have a belief to see that the proportion has increased from 45, and that would be that right there. So if you start with that first, that's fine, just as long as you write this correctly. So Max, what's the missing piece of my null hypothesis that I need to write up here?
Well, I'm not really sure.
Okay. Megan, what do you think?
Is it less than or equal to?
It is less than or equal to. Okay. Now remember, we're looking for opposites. All right. Before we had equals and we had is not equal. This is a two-tailed. This is not what we're doing right now, but I'm showing this to show the similarities and patterns. These are essentially opposites. It is either equal or not equal to. These are very much kind of opposite. Greater than 0.45, less than or equal to. And remember that equal sign will always show up in the null. Some sort of equal sign, whether it's this or this, will be in the null. and this is one of these few times in life we can say never, the equal sign will never show up in the alternative hypothesis. Never, never, never. Okay? So we've done step one, which is one of the biggest differences in the two-tailed and the one-tailed. We'll stick with black. Okay, cool. Step one, we've accomplished that. Step two, choose a level of significance and sample size. We have an alpha of 0.05. We have an N of 400. That hasn't changed. Since we're messing with N, we know by now, we've memorized it, that P equals 0.52. All right, cool. Remember critical value, so we're going to determine a rejection and non-rejection region. All right. I think I missed something. Appropriate test statistic and sampling distribution. Well, test statistic, again, for Z. Is that right there? Okay. And our distribution, again, if we're rolling with P-pop, we're rolling with the Z all day long. All right. So where the alternative, which side this is focused on, or, okay, so when we write the alternate hypothesis, we're going to write P-pop here. And the direction of this symbol is going to tell us which side of the distribution we're focused on. So on a one-tail, we're only going to have one rejection region. And that's going to be right here. So the rest of this whole thing is do not reject. Now, critical value time. Okay. We know how to compute this. We'll get to that in a second. All right. But just like we did before, we need to determine what this value is down here so that we can set up our decision rule for our T statistic, or excuse me, our Z statistic that we're going to compute here in a second. Meaning that if this value is greater than and falls in greater than that value, we're going to reject the null. But if it's less than, we're not going to reject. Do not reject. So we need to go back to our hack table. Remember, when we're dealing with critical values, we need to use our hack table, at least for the Z distribution. Okay, so I'm going to get out of here and pull up my hack table. Okay. I don't go over here. That's two-tailed test. I go over here, one-tailed test. I go down here, 0.05. That's my level of significance. And I'm going to grab that number right there, 0.1645. Now, I know it says plus or minus, but on a one-tail, I got to know which end of the distribution on, because I'm only going to have one critical value. It's either going to be a positive 1.645 or negative 1.645. In this case, it's going to be a positive 1.645. And just to check myself, I go down here, and yeah, I'm still working with population proportions, so I'm good to hook. We'll go back here, pull up my stuff, keep rocking. So this value down here that goes in this box is 1.645. That means that if my test statistic is more than that number, I'm going to reject the null. If it's less, I'm not. I compute this away. It's the same number we've gotten this whole time, which is 2.4. 814. And because this value is more than that value, I'm going to reject that sucker. All right. Now, before we move on, something I failed to highlight. On the two-tailed tests, we did the same problem with the critical value method, and then we did it with the p-value method. And you notice in both cases, we reject the null. That is because it's just a different way of skinning the cat. But the bottom line is, if the null should be rejected, it doesn't matter what method you use. Now, so I'm not saying that when you do a one-tail that you should have the same result as if you had a two-tail. That is not what I'm saying. I'm saying that if you have a two-tailed test, it doesn't matter whether you use a critical value or p-value, you should get the same result. And so make sure you understand my logic here. Now that we've done this with a one-tail and rejected it, we should also reject it when we do it with a p-value. Okay, so we're going to go and do a p-value and see if that happens. But we should know that going in. Okay, before I go on, any questions on this method I've just covered? One tail, critical value.
I have a question about like the whole thing in general.
Mm-hmm.
When do you know how to use critical value versus the other one? I
The
can't think of it right now.
p-value.
Yeah.
So the short answer is, in the real world, it's your choice. There might be some preferences in academic circles. I've seen p-value used more than critical value, but the truth is they do the same thing. And
Okay.
in terms of the test, I've been asked before, well, are you going to let us choose? No. I will tell you, I want you to do this using a critical value. I want you to do this one using a p-value. And that's not to play games with you. I want you to be able to do it all. But remember, when I say it all, I'm really talking about 12 different situations that have a lot of commonality. So I think that was Hannah. Hannah, did that answer your question?
Yeah, thank you.
Okay, super. You're bet. All right. One last problem, and then we'll call it. So all right. So same problem. Okay, one tail. What's different this time? We're doing a p-value method. Let's just go straight down to business. State the null and alternative. HO, P-pop, H1, P-pop, point, sorry. Now, I'm going to take this opportunity. You know, I've seen this happen, and it's understandable, but you just need to prevent yourself from doing this. Folks read the whole problem, which they should, but then they start getting kind of, you know, like, for example, they go ahead and they compute P, and they want to put the value for P right here. Don't do it. Don't do it. The value here for the null should be the value that's associated with the null. The value down here should be the value that's associated with the null, because the alternative is the opposite of the null. So these should be the same. These should be the same. The only difference between the two is going to be this and this, or whatever it calls for. Okay. So again, in the spirit of Ice Cube, if you have different numbers here, you know, 0.45 and 0.47 or whatever, stop. Okay. One of them is incorrect. if you have P here, you're on a bad road. If you have X here, again, you're on a bad road. All right. You got a 50% chance of being correct. It's either going to be P pop or it's going to be the mu. All right. But the main thing is to figure out and be able to read problems and be able to frame. Okay. Enough said on that. That was step one. Level of significance, alpha 0.05. P, we're not messing with P yet. Sample size is 408, or excuse me, 400. All that hasn't changed. Appropriate test statistic, we're rolling with the Z, and therefore we're rolling with the Z stat. And if you're like, oh, okay, this is very redundant. Well, I mean, I don't know if that's necessarily a bad thing. Sometimes, you know, swinging a golf, I don't even know why I use golf analogies. I hate golf. But swinging a golf club or swinging a tennis racket or deadlifting weight or doing something, you know, world-class athletes do this multiple times. So there's no reason we shouldn't and can't. Okay, compute the sample data. We got that 0.52. Compute the value of the test statistic. We're just going to go ahead and do all that. We know that it's 2.814. Okay, just to get a different color up on the board. And we know, and now compute the p-value. Okay, well, just like we did before, we could go to our z-score table. If we do that, we need to know what we're talking about. This, the way that this is oriented tells us we're out here on the right end of the distribution. So if we go to the z-score table and turn this into a probability, we've got to do a 1- to get that p-value. Okay. So there's nothing wrong with going to the z-table. We just know we need to know that we need to know to do the 1-, or we could do norm S dist and either do a true or false at the end of it. We could put 2.814. And if we put false, it's going to give us the p-value. If we put true, we got to do a 1-. And we'll get this number here, 0.00726. Because it's a one-tail, we don't do anything to that. That is the p-value. Okay, I'll just say that one more time. We don't do anything to that because that is the p-value. We don't half it. We don't double it. We don't do anything. We set up our little alligator and the fish. All right, we set up our alpha over here, 0.05. We set up our p-value, 0.007. Whichever phrase works for it. If the p-value is lower than the level of significance, we reject the null hypothesis. Or if the alligator eats the fish, which it's going to because it's bigger, we reject the null hypothesis. Either way, we reject the null hypothesis. And in this case, like Lexi said, we do have reason to believe that if this was, I'll just draw it in blue, if this was the original population proportion, actually it should be more in the middle, but we do have reason to believe that the population proportion is now greater and so has shifted out here, okay? Which would be a really good situation for us to go ahead and do a confidence interval, which I will just tell you, I'm going to ask you to do that. Okay. And we'll get reps in on that. All right. And again, to do that, we know what that formula is. From a business perspective, we know what that market looks like. All right. We know that it's greater than 0.45 with a confidence interval. It can tell us give us a guess on how much greater it is. Okay. And therefore, how many resources, how much advertising, how much potential labor and opportunity there might be out there. Okay. Because of this growing tendency to work during non-business hours. Okay. So what we just went through was the one-tailed p-value version of that. But in the aggregate, we went through really one problem modified 4 times. Okay. Now, if we hadn't modified this red letters here, we wouldn't be able to do it 4 times. We'd be able to only do it twice. Okay. But modifying this enabled us to do it as a one-tailed test. All right. And therefore got after the 4 possibilities of hypothesis tests within proportion population or populations of the proportion. What are your questions, big or small, about any of this? Way of the warrior, if it's going to snow more today, anything?
I have a question.
Yes, Kendall.
So when you say you're solving for P and you're using the Z table, you'll get the same value as if you were to use the true, right? Like if you did if you did the true on Excel, you'd get the same value on the Z table, right?
That is correct.
So I was just doing that, and when you do 1 minus that value, it doesn't equal what you get for the false.
How far off is it?
Are they supposed to be the same?
They should be. How far off are they?
So when you do 1 minus the 0.9975, you get the 0.0025, and that one's 0.0072. So it's kind of far off.
Yeah, it's kind of far off.
And I tested it with both just to see if it was just Excel, but both Excel and the Z table give you 0.0025.
Oh, and not this right here?
Yeah.
When you put in this number here?
Yeah, so if you put in that number in true, you get
Uh-huh.
0.0025, and if you do it on the Z table, you get 0.0025. But if you put false on Excel, you get the 0.00726.
I owe you an answer on that one of why that is and which one to use. So I've got to do out there. So I don't
That's
know.
fine.
Yeah.
I was just curious.
No, I'm glad we need to be bulletproof there. So
I
I'm
was
glad
just
you
curious
pointed that out.
because instead of doing it on Excel, while you were talking, I real quick just used the table and it didn't give me the same answer. So I was just confused.
Yeah. Well, it should. Maybe I'm not as solid as I should be there. Something's going on. So I'll find out.
Okay.
Thank you for bringing that up. Other questions, big or small?
I'm still kind of confused on how you figure out the statistical decision. How do you know when to reject or not reject the null hypothesis?
Okay. So, Greg, is it under a particular method or just period?
Just period, for both of them.
Okay. So for a p-value method, if the p-value is less than alpha, then we are going to reject the null. Okay. So right here, whichever number it is, 0.0025 or 0.0076 or 726, both of those are less than alpha. Now, if the p-value was, let's just paint the extreme, 0.25, after we were done with our computation, then the alligator would eat this side, okay? Or the p-value is lower than the alpha. Well, it's not. It's greater than. So we would not reject the null under this situation right here. With the critical value method, we are essentially making a decision rule. Okay, we are determining what these critical values are, and we use that with our hack table. So for example, if our critical value is 1.96 and negative 1.96, then we look at our T statistic and see if it falls into, it's either going to fall into one of these areas or it's going to fall in here. So we look at the value of our T statistic, 2.814, and that would fall out here. This area is our rejection region. This area is our rejection region, meeting this shaded spot, this shaded spot. Another way of putting that, we could say if the z-stat is greater than the critical value on the right-hand side, or the z-stat is less than the critical value on the left-hand side, then we would reject the null hypothesis. But if it isn't, we won't. Okay, so this up here is the same thing as this down here. Pearson will ask you, if assuming that I ask them to ask you, Pearson will ask you for decision rules, and that's all that really is. It's the same thing as this. Okay, so if in this case we would say if the z-stat is greater than 1.96 or less than negative 1.96, then you would reject the null. Otherwise, you don't. You fail to reject. Greg, does that help out?
Yeah.
Okay. Other questions?
I had a quick question.
Okay.
So just say, for example, instead of saying has increased, it says has decreased. Would your line on the chart be like to the left, and then instead of doing the norm S distribution false, you would do the norm S distribution true in that case?
That sounds right.
Okay.
The reason I hesitate is because now I'm concerned about using this formula because I don't want to mess you guys up. Not that we're not going to, I just want to go confirm it. But
Okay.
everything you said prior to that, Tim, is indeed correct. So if we reversed this, and if folks got to drop off or want to drop off, then, go ahead. I don't want to hold anybody up. But if we reverse this and said this and this, right, Tim? It's kind of what you're saying.
Yep.
So we would be hypothesizing that the population proportion is out here, but regardless, we would be determining this would be our rejection region down here.
Okay.
All right. So yes, is the short answer. With the exception of this, I want to check this out before.
Then in that case, if we were just using the Z table and not that formula, we wouldn't have to do the 1 minus then?
That is correct.
Okay.
And which brings up a good point. If we're doing a two-tailed p-value, I always like to go to this end first with to determine what that is, and then I multiply it by 2. Because if I go to the right, I'm going to have to, and if I go to the Z table first for this right value to determine the p-value, I'm going to have to do a 1 minus, but here I don't have to.
Okay.
And then so all I got to do is grab that value and then multiply by 2 on a two-tailed. On a one tail, I just find out that value and I can stop there. I suppose, kind of like our earlier discussion, I could cheat. Tim, we had this discussion seems like about 5 years ago. If I know this, I need this value. Let's say I need this value. I have a one-tailed out here. Well, I could cheat and go to this side of the table. I just need to know that value and make it negative, but it's all the same. You know what I mean?
Mm-hmm.
That goes back to our discussion. Hey, if I stole one side of your Z table, would it matter? And it probably wouldn't. You'd probably still be able to fight your way out of that, I would think. Okay, so does that answer your question?
Yeah, perfectly. Thank you.
Okay. All right, what else? Anyone?
So for the p value equals, it's basically 1 minus the z value, and then for two tail, you basically just take whatever that value is and double it.
So when you said 1 minus the Z value, I don't know if I would put it that way. If I'm trying to determine a p-value out here on the right, Greg, and I look up a Z value like this, I'm going to have to do a 1 minus because I'm out here on the right-hand side of the table to find out that p-value right there. If I'm doing a two-tailed, I can do, if I'm doing a one-tailed out there, then, you know, I need to find this, go to the Z table, do a 1 minus, and find the value. And that would be the p-value. I think that's what you're asking. There's just the way you said it. Maybe I didn't understand it or heard it wrong. Does that help out?
Yeah.
Okay. Other questions? All right. I will do all my normal things, post this video. I owe y'all a more solid answer on the norm dis false stuff. So I'm going to run that down here. Hopefully that won't take too long, and I'll probably put something out to you. I'll hang out if folks still want to ask questions or whatever. Otherwise, y'all have a great weekend. I look forward to your projects, and be safe. Take care.